This is the video for Unit 3, Section 2, Types of Reactions. In this video, I'm going to go over first the structure of chemical reactions. These are things that we've seen before, but I want to give a name to certain components of those reactions. And then we'll go through the 5 types of reactions listed on screen, along with a couple of examples. So, let's start with the structure of chemical reactions. All chemical reactions are going to be laid out the same way. We'll start on the left side where we have multiple pieces, well, usually multiple pieces, and we call these the reactants. So in this case, this H2 and this O2 connected by a plus, these are the starting ingredients, which again we call reactants. After the reactants, we put an arrow, usually pointing to the right. This arrow shows us what the end result of the reaction is, and it shows that the reactants on the left, they're going in the direction of the arrow, so they're becoming whatever the arrow points to. And on the right side, we have our products. These are whatever is left over after the reaction. This is what usually we're trying to create. All chemical reactions are generally going to look like this. A left side with the things we start with, the reactants, an arrow pointing to the right, and then our products on the right, the things that we create. We don't have to think of this just in terms of chemistry. We could think of this in terms of, say, baking. Let's say I wanted to bake a cake. My ingredients, eggs, flour, sugar, maybe a few more things, they would be on the left side of my chemical equation, connected by plus signs. I would use the arrow to say they're becoming something new, and in this case, they would become a cake. But it doesn't have to just be baking or chemistry either. This could really work for a lot of different things. Let's say you wanted to make a car. You would say that you need tires, a frame, a windshield, probably a few other things like an engine. And these objects are becoming, shown with this arrow, a car. All chemical reactions are going to be laid out this way. So let's also quickly break down the parts in this chemical reaction. It's going to be easier to see how these reactions work and how the reactants change if we see them as individual pieces. So right here I've color coded my different elements, my hydrogen as an H, my oxygen as an O, and I show that it's still broken up into 2 pieces in this final product, but in reality this final product is one piece, it's one compound. Just know that every element is either 1 or 2 letters, and it always starts with a capital letter. So because this is a capital H, and because this is a capital O, they are 2 distinct elements. I will call out a couple of examples of that in this presentation. And what we'll see is in a lot of these reactions, these elements are going to switch positions or switch partners with the reaction. So they're going to form something new, but they do that in a predictable way. And the last thing I want to go over is just that we have some pieces that stick together even though they're multiple elements. And these are typically our polyatomic ions. These are composed of multiple elements. See this NO3 here? Because they're both capital letters. We have a capital N for nitrogen and a capital O for oxygen. But notice that on the right side of the equation, they are still sticking together. They're acting like one piece. So these polyatomic ions, they act as one piece, kind of like they're sticking together. All right, that's enough of that background information. Now let's talk about types of chemical reactions. We have 5 types of reactions that we'll go over, and they encompass a few different things. I have 3 reactions on the right here. Mute this. You'll notice that in the top right, we have that super bright reaction. It kind of looks like something's catching on fire. In the bottom left, we have a fire as we'd picture it. And in the bottom right, we have something that's sizzling in a tube. We've talked before about how these are all chemical changes, but now we're going to actually classify them as these different types of reactions. The first type we'll go over is called a synthesis reaction. The second type is a decomposition reaction. The third is a single replacement, followed by the fourth, a double replacement. And finally, we'll talk about combustion. Just know that this is not a complete list. There are reactions such as acid-base neutralizations and many more that we will not cover. But these 5 that we will cover, synthesis through combustion, that covers a lot of the general chemical reactions. So let's get into it. Our first type of reaction is a synthesis. And on the last screen, I actually showed you this in this video. This video is taking sodium, this Na, and adding it to Cl, or chlorine, to make sodium chloride. And that's what a synthesis reaction is. It's when 2 or more reactants combine just to form one product. So I see this Na over here, one reactant, combining with a second reactant, and making that product, NaCl, on the right. Sometimes this will be called a combination reaction. They're the same thing. A synthesis reaction is the exact same thing as a combination reaction, although combination might be a little more easy to remember because we're just combining these elements. Also, since I said I would call it out, notice that Na, a capital followed by a lowercase, that's one element. Same with Cl, a capital letter followed by a lowercase. Some examples of synthesis reactions. If we were to put hydrogen and oxygen together, we would get as a product H2O. This reaction is extremely explosive if done at normal temperatures with the two gases, and it's not that easy to show. Another example would be iron, Fe, plus sulfur, S, are two reactants, and they're becoming FeS, or iron sulfide, as our product. The main clue in all of these reactions to know that they're a synthesis reaction is that there is only one product. When we only have one product and multiple reactants, we know that we have a synthesis. We're synthesizing one product. And we can actually see an example of this bottom reaction, iron plus sulfur, right here in this video. Very fiery, a lot happens, but believe it or not, you're only forming one product. Just that iron sulfide. Let's move on to our second type, decomposition. In this case, I have H2O2, or hydrogen peroxide, breaking up into water and oxygen gas. A decomposition such as this is one where one reactant, H2O2 in this case, breaks apart into multiple products. In this case, H2O or water and O2. It's sort of the opposite of a synthesis reaction. One reactant is breaking into multiple products. And remember, in synthesis, multiple reactants were becoming one product. So these are the opposite of one another. And we actually know this reaction, or we can see why we have to be careful about it. Hydrogen peroxide, as you may have seen in like your bathroom or your medicine cabinet, it's in this brown container because one thing that can make it decompose is light. So you want to protect it from light so it doesn't become water and oxygen. That wouldn't be very useful. Let's look at 2 more examples. One example is if we took this silver chloride, or Ag, one element, Cl, a second element. We took this reactant. It would break down into Ag, or just silver, and chlorine, Cl, as products. So it's one reactant breaking into 2 products. We can also see this reaction, copper carbonate. One reactant is breaking into 2 products. And that's really as simple as decomposition gets. One reactant breaking into multiple products. The third type, and this is going to be a little different than what we saw before, is called single replacement. What we'll see is that a single replacement reaction is when one reactant switches with its partner with a different single element. If we look at this example here, this hydrogen, this orange H, is switching positions with this zinc, this blue Zn. We sometimes call this a single displacement reaction. It's really the same thing. I'll be using single replacement for this section. I want to look at this a little more closely though, because it's easy to get lost in these letters. Picture each letter as just a single, solid sphere atom. Notice the colors match in this case. we can see in this bottom example that the blue zinc is replacing the orange orange hydrogen, in this pair. So really what we're doing is we're swapping out blue for orange in this pair. And on the right, we can see that we have a single orange and then a paired up blue-red. A couple more examples. If we look at this example, NaCl plus Ag. The Ag is going to replace the Na as the partner with Cl, and Na is left by itself. Another example, Ag plus NaNO3. Notice that NO3 stays together. It's one of our polyatomic ions. This Ag and this Na really just switch spots. The Na is by itself, and the Ag is paired up with NO3. Our clue that a reaction is single replacement is that one element is alone on both the reactant and product side. So if I look at this bottom example here, I can see that on the product side, Na is by itself, just one element. And on the reactant side, Ag is by itself, just one reactant or one element by itself. If there's one element by itself on both sides, we probably have a single replacement. But just check to make sure that we've replaced a single element when we go from reactant to product. Our last type, it's like single replacement, but a little more difficult. It's called double replacement. In double replacement, that reaction occurs when both reactants switch their partners. It's a little hard to see in this letter format, but what we can see is that this Zn, the zinc, is staying where it is, and the H is staying where it is. The Cl and the F are trading partners. When we go to the right, instead of ZnF, we have ZnCl, and instead of HCl, we have HF. They switched their partners. And just like single replacement, you can sometimes call this double displacement reaction. Again, let's look at that as atoms. You can see we have blue-green and orange-red on the left. And on the right, we've switched partners. We have blue-red and orange-green. So we basically take everything and just change partners. A couple examples. We can see salt, NaCl, plus AgBr. Notice Ag partners up with Cl, and Na partners up with Br when we get to the product side. So they've switched partners. And AgCl plus NaNO3. Notice that NO3 is acting like it's one piece. It's its polyatomic ion. The Ag is switching with the Na. We now have NaCl on the right and AgNO3 on the right as well. And these are our double replacement reactions. Our last type of reaction is called combustion. And a combustion reaction is when oxygen, or O2, is added to another reactant. Usually, but not always, this forms two products: carbon dioxide, or CO2, and water. However, there is a third product, but it's not an actual chemical. We usually see light and heat come from this reaction. If you think about combustion, you may think about, say, like a fire. A fire is taking some carbon compound, or CHO compound, and adding oxygen to it. And it breaks it up into carbon dioxide and water. So a fire is one type of combustion reaction. Some examples of this as chemical reactions: if we take C8H18, or octane, and we add some oxygen to it, we are going to make carbon dioxide and water. If we take isopropyl alcohol, or C3H9O, and we add oxygen to it, again, we will see carbon dioxide and water as our products. However, there are some other kinds of examples. If we take iron and add oxygen to it, we get iron oxide, or Fe2O3. If we take a different metal like zinc and add oxygen to it, we get ZnO, or zinc oxide. The reason why these are slightly different, notice that although the reactants look the same, one reactant reacting with oxygen, we have a different set of products. We don't have CO2 and H2O. We don't have carbon dioxide and water. The products for common combustion reactions, they don't need to be CO2 and H2O. In this case, these combustion reactions, they're also kind of synthesis reactions. We're adding our two reactants together to get one product. I would say that these are more indicative of a synthesis reaction because they're not the typical kind of combustion we would picture. However, they technically do fall under the same idea of adding oxygen to a reactant. And that is all 5 of our reactions for this video.